Hi, and welcome to the Workshop 4 on Mplus. This week we will be going over path modeling and some basic structural equation modeling in Mplus. During every workshop we have built upon what we discussed previously, and we're going to continue to do that. Although all of the delivery of the workshops is going to fully online, I want to continue to provide you with high quality instructions so you can find ways to use this marvelous program for your own modeling needs. So far we have discussed how to access Mplus on the remote desktop, and we've run models reflecting all the commands in Mplus syntax. And I've pointed out some of the features of Mplus that are unique and might be overlooked. Finally, we discussed many examples of regression models. And so this week we're going to be talking about path modeling and SEM. Structural equation modeling represents a collection of methods that use the covariant structure of data to test quantitative relationships between variables. In SEM, we have measured variables and we have factors. And SEM allows the researcher to include many more variables and relationships in a single model. It allows researchers to estimate measurement error and allows us to do a lot of latent variable modeling. Now, path modeling represents a subset of SEM, and path modeling use only observed variables and no measurement models. Now, today we're actually going to have two path models and one full structural equation modeling model, but it's going to be a model that's very small. Here are our demos for this week. We're going to have a path model, as I mentioned, with 5 measured variables with a mediated effect. We have a path model where we are going to be asking the questions about how to choose a model that has the best fit. And then we're going to be talking about an SEM model, and we're going to be asking questions about how to set up the parameterization with different marker variables. I've included a Word document that looks kind of like this, that has all of this information on what to use for each of the demonstrations. I recommend that you get that handy so that as you go through this, you'll know exactly what files are needed. And again, there's going to be a zip file, so go ahead and download that zip file and have it available to you for, here it is, here's my reference, have it available to you on in remote storage on your hard drive. If there are any changes to how you can access Mplus through the remote desktop, I will inform you of that. I just recently reached out to IT to find that out. All right, so here are some of the resources I am using this week. I'm using some data examples from each of these, as well as a data example from some work that I have done previously in actually some of my coursework when I was getting my PhD. Each of these has a link. I would highly recommend getting each of these books. I have one more book at the end of our discussion today that I'd like to go over with you. Although this slide presentation has 32 slides, I'm not going to go through it all in one chunk. I am going to break it up into several parts so that you can watch it in parts. Hopefully those divisions will make sense and will not be just in mid-sentence. So we'll see. Here it goes. All right, so we have talked about multiple regression before, and all of these X variables are called exogenous because they're not affected by something in the model, and the Y variable is called endogenous because it is affected by all of these terms in the model. And we can represent this as an equation. And we know always, even when these variables are observed, that this regression with the coefficients that are estimated is not going to be exact. And there will be some residual, and that's what the E refers to as the residual. Now we're going to examine models with many paths representing more than one regression. Often the convention is to represent these in a path diagram like you see here. And actually this is one of the path diagrams we're going to be talking about this week. And typically you provide this rather than equations, although we could also represent these with equations. Now look at slide 9. In slide 9, I'm going to go over some of the basic rules for diagrams. So a circle is really considered a latent variable, and some of the circles could be a latent variable that informs or predicts the observed variables, and some of them may be the result of modeling and being a disturbance or error in the latent variable, something like this. So here's the latent variable and here's the error. You also have observed variables. So observed variables are the variables that are in your data set. And so they are the variables you've actually measured and collected. And then you can also have measurement error in the observed variable, and it will look like that. Now we will talk about the paths, which represent the regression coefficients. So this is a one-directional path. So for example, if we go back, I'm going to go back to slide 7. You see these one-directional paths, x1 and x2 and x3 to y, which means that y is a function of those variables. And we see in this case, those are one-directional paths. If you have a two-directional path, either straight and sometimes curved, that represents a correlation. So that's just a correlated effect. It's not actually a regression. And then sometimes you actually have a feedback relationship, and those are called non-recursive. I'm not joking. You'd think it would be called recursive, but it's not. It's called non-recursive. And it means that each of these variables is strong enough to have some predictive power on the other one. Now this week we're going to be talking about mediation. And mediation is a regression, a series of regression equations amongst 3 or more variables. I'm going to show the most basic, simplest case here, which is 3 variables. We have x, m, and y. So m is predicted by x, and y is predicted by x and m. And you'll see that you have an indirect effects, you have a direct effect, and then you have a total effect. So these small letters here represent the path coefficients. And here's another way of looking at it here. As I mentioned, because we are doing this as a path model, you are going to see some error terms here as well. And what this means is that x has some function on y. So y is somehow affected by change in x, but part of that change is mediated. That means it's changed in some way. It's either a causal effect where x causes a change in m and m then has an effect on y. It may be a causal effect as well. But you do expect that x is actually functioning on m, changing it, and m is functioning on y and changing y. And that is a mediated effect. Now, in our next diagram, we have several mediated effects, but they're really complicated. I'm going to go through the whole model. Again, this is a boot camp type workshop, and so this first model, each of the models are pretty complicated. So here's our first model. Demo 13, McDonald and Cleland investigated sentiments towards unions. We have a data set with these 5 variables collected: age, years, difference, support, and sentiment. And we want to know what these impact, these variables of age, years, difference, and support have on sentiment. And so in doing this, I want to talk a little bit about model identification. In this case, we have 6 path coefficients, we have 3 residuals, we have 1 correlation, 2 independent variable variances. And so if you add those all up, that equals 12 variables that the modeling procedure must freely estimate. So we have to have enough information in order to be able to do this. You remember this from basic algebra. You have to have as many pieces of information as you have unknowns in order to be able to solve for a single solution. And so in this case, we have 5 variables. And so in a variance covariance matrix, and I recommend you actually go back and look at the data set to see this, you're going to have 15 values. And this is how you calculate it. You have 5 variables, so 5 times 6 over 2 equals 15. If you have 12 variables and 15 pieces of information in your variance-covariance matrix, you have 3 extra pieces of information. That means 3 degrees of freedom. And that's this case, the model is over-identified, and that is a great thing. So this is considered a saturated model. Now I want to talk briefly about model fit. If the model fits the data, the chi-square test should not be significant. And this means that the sample variance-covariance matrix is not significantly different from the model-implied variance-covariance matrix. So they're not statistically significantly different. And that's a good thing, because so that means what the model has estimated fits what the real data says. Now, the problem with model fit using chi-square is that this is a large sample technique, and oftentimes if you get over 200 elements in your sample, the chi-square test will be significant, and that's just due to the large sample size. This is one of the challenges of structural equation modeling, and we'll talk about that again at a later time. With that introduction, I am going to stop here and start videoing on the next video the actual solution to this demo 13.